Hi everybody, so today we're going to talk about solving different types of equations. It's mostly a review of different solving techniques you should have seen before. Okay, but before we do that, I want to review one piece of vocab. Okay, okay. So we need to talk about what an extraneous solution is. So an extraneous solution is a solution you get from solving correctly but when you substitute it, okay, it doesn't actually work. So it's something that you're not, it's not coming from a mistake, it's coming from you solving correctly. But when you go to plug the solution back in, it doesn't actually work. It's not really a solution. Okay, so we're going to need this when we talk about the first type of equation that we're going to solve. Okay, so we're going to talk about solving rational equations. So first we'll go over what you do to solve rational equations, and then we'll do an example. Okay, so the first thing you do when you're solving rational equations is you want to find the LCD of all fractions. Okay, then you are going to multiply both sides of the equation by the LCD. Okay, now the point of this method, and I'm going to put this as a note, is that you should have no fractions left after you multiply by the LCD. Okay, so the point of this method is to clear away the fractions so that you can solve. Okay, so after that, you are going to finish solving normally. Okay, and then we're going to do what we talked about with the vocab, and we are going to check for extraneous solutions. Okay, so I wanted to point out that this is not a check for mistakes. It's not an optional check. You have to do this, and it's because you can't detect extraneous solutions except by checking your solutions at the end. Okay, so let's do an example of this method. Okay, so the first thing we're going to do is look at all of these fractions and we're going to determine the LCD. Okay, so only these two terms have denominators, okay? And these denominators don't have any common factors. 3x and 3x plus 1 look similar, but they don't have any common factors, okay? And when that's the case, the LCD is just the product of the two. So we'll have 3x times 3x plus 1 as our LCD, okay? So that's our LCD. Now we're going to multiply everything in our equation by this LCD. Okay. Okay, now I'm leaving myself some room so that I can write in what we're going to multiply by. Okay, so here we're going to multiply by our LCD. Here we're multiplying by the LCD. Here we're multiplying by the LCD. Okay, and then on the right side of the equation, same. Okay. So each term, right, left side and right side is being multiplied by the LCD. Okay. So now you're going to cancel anything that's a common factor. So we have this 3x in the numerator and this 3x in the denominator. So this is going to cancel with this. Okay. And my first term is just going to be 3x plus 1 times 4. Okay. Now this 3x plus 1 is going to cancel with this 1 in the numerator. And I'm going to have 3 times 3x. Okay. Then here, there's nothing in the denominator. So nothing cancels, and I just get 2 times 3x times 3x plus 1. Okay. And on the right side of the equation, 0 times this stuff is still 0. Okay. So now I'm actually going to multiply this all out so that I can combine like terms. Okay. So I'll have 12x plus 4. Here I'll have 9x. Oops, that's a plus. Here I'll have 9x. Here I'll have 6x times 3x, which is 18x squared. And then 6x plus times 1 is 6x. Okay. Okay, so that's the main part that has to do with being a rational expression. You find the LCD, multiply by the LCD to cancel all the denominators, and then you're left with an expression like this. So now at this point, we need to determine what kind of equation we're talking about. You can see we have x squared here. So this is a quadratic equation, and we're going to move everything to the left side and try to factor it. Okay. So I'm going to combine my like terms and write them in descending order. Okay, so my x squared term is just 18x squared. Now I'm going to combine my x terms. So I have 12x and 9x, that's 21, plus 6, that's 27. Okay, and then my constant term is 4. Okay. Now, as is always the case, right, you want to try to factor this. Okay, now we're going to look for common factors. 18 and 4 have a common factor of 2, but 27 doesn't. 18 and 27 have a common factor of 9, but 4 doesn't. So there's really no common factors here. Okay, so we're going to use the guess and check method of factoring. Okay, so I'm going to try 6x and 3x first. Okay. And then I might try 4 and 1. And because I have a plus here and a plus here, I have to put plus and plus. Okay. Now 6x times 3x is 18x squared. That's good. 6 times 4 is 24. Plus 3 is 27. So our first guess was right. If your first guess was not right, then you just keep guessing. But I did want to point out that you can't have, once I picked 6 and 3, I can't split up this 4 into 2 and 2, okay? Remember, when you're factoring like this, if 6x and 2 are here, they have a common factor. That's not allowed because this expression doesn't have a common factor, okay? So that's a way to cut down on the number of things that you are guessing, okay? So this would give me x equals negative 1/6 and x equals negative 4/3. Okay. All right. Now, let's talk about what that finishes the solving process. So let's talk about what we're checking for with rationals when we're checking for extraneous solutions. Okay. So what you're checking for, you can see from the very beginning, you don't want any of the denominators to be 0. Okay, so if you plugged in 0 here, for example, this would make that fraction undefined, and that's an extraneous solution. Okay, so like I said, this one, the only forbidden solution would be x equals 0, and here it would be negative 1/3. Okay, so if we check our solutions, they're not 0 or negative 1/3, so these are good solutions. Okay. All right. So let's move on to a different type of equation, okay, although we still will be talking about extraneous solutions. So let's talk about square root equations. Okay, so square root equations have a very well-defined process. The first thing you're going to do is isolate a root. Okay, if there's more than one, you pick one of them to isolate. Okay, then you're going to get rid of the square root by squaring both sides. Okay, once you've squared both sides of the equation, okay, you're going to check if there are any square roots left. Okay, so if you still have a square root after steps 1 and 2, then you repeat those steps. Isolate the square root, square it again. Okay, then you are going to solve normally. Okay, and the last step, just like we saw in the previous example, is going to be check for extraneous solutions. Okay. All right, so let's look at an example. Okay, so the first thing we want to do is isolate one of the square roots, okay? And just a tip, this isn't necessary, but usually when I'm picking which one to isolate, I pick the more complicated of the two. So because this one has 2 terms, this one only has 1, I'm going to isolate this square root. Okay. Now I'm going to square both sides. Okay, and this is very important. When you get to this step and you're squaring this side that has 2 terms, you have to write it out and actually square it correctly. You have to FOIL it out. You can't just square the 2 of them separately. Okay, so over here, square root and square are going to cancel. We'll get x minus 7. Okay, and over here, we would get 49 minus 14 root x plus x. Okay. All right. So this is step 1. Here's step 2. Okay, and now you guys can see that we do still have square root of x. So I'm going to try to isolate this root x here. Okay, so I'm going to subtract x from both sides. Okay, now I'm going to subtract 49 from both sides. Okay, and now I'm going to divide both sides by negative 14. Okay, so now that I have my root x isolated, I'm going to square both sides again. Okay, and I get 16 equals x. Okay, now this is an important step when it comes to solving radical equations. When you check, you want to check in the original equation. Okay, so we are going to check our x equals 16 in our original equation, this one here. Okay, so I have square root of x minus 7, okay, plus root x equals 7. Okay, so I'm going to plug in x equals 16. Okay, so 16 minus 7 is 9. Oops. Got a little ahead of myself there. 3 plus 4 equals 7. Okay, that's true. Okay, so what that means about our solution is this is really the solution to that equation. Okay. All right. So let's try one more of these types of equations. Okay, so the first thing we're going to do is we're going to isolate root x. Okay. Okay. Now I want to take a second at this point to say you don't have to isolate the root itself. You just need to isolate this term. Okay. And we're actually going to square it at this point just so that we don't end up having fractions and then having to clear them and that kind of thing. Okay. So we are going to square this whole term. Okay. And we're going to square this whole side. Okay. Now when you square this, you are squaring both the root 2 and the x, so you'll end up with 4x. Okay. And here we're going to have 225 minus 30x plus x squared. Okay. Now, at this point, again, we're done with the square root part, and we're trying to assess what type of equation we have. So we have this x squared. It's a quadratic. We're going to move everything to one side and factor. Okay, so this will be x squared minus 34x plus 225. Okay, I'm going to factor. Okay, so I'm looking for something that multiplies to 225 and adds to 34. So I think that's going to be 25 and 9. Okay, and that will give me my two solutions, x equals 25 and x equals 9. Okay. So another thing about extraneous equations or extraneous solutions, you do have to check both of the solutions if you end up with two like we did in this example. Okay, you can't avoid that. You have to check them both and you have to check them separately. Okay, there's no way to detect extraneous solutions like I said. You have to just plug them in. Okay, so remember our original equation was this. Okay, so we're going to check x equals 25 first. So we'd have 25 minus 2 root 25, and that equals 15. Okay, so this is going to be 25 minus 2 times 5, which is 10. Is that 15? Yes, it is. Okay, so this is certainly a solution for this equation. Okay, so let's check x equals 9. Okay, 9 minus 2 times 3 is 6. Okay, so 9 minus 6 is 3. It's not 15, so this is a false statement, okay, which means that x equals 9 is an extraneous solution. Okay. So this is what I mean by you can't tell the difference between a good solution and an extraneous solution. There's nothing that gives them away. It's not like negatives or positives or anything like that. So you just have to plug them in and check. Okay. All right. So that about covers the square root equations. So let's talk about power equations. Okay. So first, let me remind you what makes something a power equation. Okay, so what makes something a power equation is, so n and a are real numbers. Okay, so what makes something a power equation is that you have the variable here and then you have a numerical exponent. Okay, this is to differentiate it from exponential equations where you have a numerical value and then a variable exponent. Okay, so this is a time where the exponent is a number and the base is the variable. Okay, so for these, our plan is to okay, so first we're going to isolate the expression with the variable. Okay. Then you are going to change to radical form if that applies. Okay. Then you are going to root to get rid of exponent. Just like you would use a square root to get rid of a square, you can use a cube root to get rid of a cube, okay, etc. And then you are going to use a power to get rid of a root. Okay, now we saw this in the square root equations, right? When you have a square root, you would square both sides. Now, if you have a cube root, you would cube both sides, fourth root, fourth power both sides, okay? So we're just going to do it in that order, okay? We're going to root first and then use the power, okay? Then we're going to finish solving if that's necessary. Okay. And most of the time with these, you don't need to check for extraneous solutions, okay? So I really only am listing the check for extraneous solutions on types of equations where you absolutely have to check for them. Like I said before, you're not checking for mistakes, so you really need to do that when it's part of the problem, okay? So let's see an easy example of this. Okay, so this is one that you guys have definitely seen. Okay, but it incorporates what we talked about with complex numbers, so I just wanted to talk about this. Okay, so the first thing we're going to do is isolate the variable with the power. Okay, so we have x squared here, so we're going to subtract 1 from both sides and then divide both sides by 3. So that's step 1. Okay, now we don't need to change this to radical form because we don't have a fractional exponent. Okay, so we're going to use a root to undo the exponent. So we're going to use square root because it is a square power. Okay, and with even roots, you are not going to forget the plus or minus. Okay, so you need the plus or minus when you're talking about even indexed roots. Okay, so square root of x squared is x. Okay. All right. Now, square root of -1, we know that that's I. Okay. And then we can't simplify root 3. Okay. So just to put this into the standard form that we talked about for complex numbers, right? You would have plus or minus 1 over root 3I. Okay, so the real part is 0 and the imaginary part is either positive 1 over root 3I or negative 1 over root 3I. You're actually getting 2 different solutions here. Okay, all right, let's look at a more complicated example. Okay, so the first thing we're going to do is isolate the variable with the exponent by subtracting 1 from both sides. Okay, and now we're going to get rid of this exponent by cube rooting both sides. Okay, now because we're using an odd index root, we don't need plus or minus. Okay, now the cube root of x cubed is x. Okay, and the cube root of -1 is -1. Okay, all right. So let's look at some examples of those that do have fractional exponents. Okay. Okay. Now here's our expression with our power. Okay. So we don't need to isolate it because it's already isolated. Okay, now in this example, because we do have a fractional exponent, we are going to change this to radical form. Okay, so remember the denominator of the exponent becomes the index. Okay, and then the numerator of the exponent is the power. Okay, so we're not doing anything to both sides of equations, we're just rewriting this exponent as a radical. Okay, now we're going to take care of the exponent first. I suggest you do this because it's easier to take a root and make things smaller than it is to cube 25 by hand. Remember, you guys don't have calculators, so you don't want to be multiplying out in your head 25 times 25 times 25. Okay, so to get rid of this, I'm going to square root both sides. Okay. Now the notation of this is a little cumbersome, but I want to be clear about what we're doing. Okay, and because we're using an even indexed root, I'm going to put my plus or minus. Okay, so square root of a square, those cancel. Okay, now I'm going to get plus or minus 5. Okay, now I need to get rid of my cube root, and I'm going to do that by cubing both sides. Okay, so okay, so the cube of a cube root is just the radicand. Okay, and over here I'm going to get plus or minus 125. Okay, now I think it really makes sense to split these two answers up so that we can solve them separately. So I'm going to get 2x plus 1 is positive 125, or 2x plus 1 is negative 125. Okay, we didn't split them up before because there was no extra steps to take after you got the plus or minus. But here, when we're going to subtract 1 and then divide by 2, it's really going to make it easier to have them both split up. Okay, so this will give me 2x equals 124, and then x equals 62. Okay, and then here I'll get 2x equals minus 126. Okay, and then x equals minus 63. Okay, all right. So let's look at one more example of the power equations. I want to talk about what happens when you have a negative exponent. Okay. Okay. So now you guys know that negative exponents put something into the denominator. So that's the first thing I'm going to do. Okay. And now I'm going to try to isolate this expression. Okay. And the technique I'm going to use is cross multiply. So I'm just going to make this over 1 and then I'm going to cross multiply. Okay. And then I'll need to divide both sides by 9. Okay, so now we have an equation that's a lot like the previous example, so I'm going to change it to radical form. Remember, the denominator becomes the index, okay, and the numerator becomes the exponent. Okay, now I'm going to get rid of my exponent by taking the root, so I'll do square root. Not forgetting about plus or minus. Okay, square root of a square, that cancels, and I get fifth root of x. And here I get plus or minus 1/3. Okay, and then the last thing I need to do is get rid of the fifth root by using the fifth power. Okay. Okay, now fifth root and fifth power, those cancel. And here I'm going to get plus or minus 1 over 3 to the fifth, which is 243. Okay. All right. Okay, so one more type of example to go over. I want to talk about some examples of solving using factoring. We already reviewed factoring and did some pretty difficult examples of factoring types. So we are just quickly going to go over some examples of using factoring to solve. Okay, and we're not going to do any basic algebra type examples. We're going to do some more complex examples based on the type of factoring that we talked about. Okay, now anytime you're going to solve using factoring, you have to put everything on one side. You can't solve using factoring unless all of your terms are on one side and the other side is 0. Okay, now while I'm looking at this, okay, I don't need to factor out the lowest exponent, excuse me, because 4 doesn't have a variable, so there's no common factors of y here, okay? Then when I look at this, I can see that it's quadratic in form, right? 2/3, 1/3, and 4. So you're welcome to use a u substitution, and if you do, I suggest using the u substitution, u equals y to the 1/3. Okay, so if you're going to use a u substitution, go ahead and pause the video, do the u substitution so that you can see how your factors are going to look. Okay, I'm going to factor directly. Okay, so I'm looking for something that multiplies to 4 and adds to -5, so I think I'll have -4 and -1. Okay, so just like with normal solve by factoring, I'm going to set each of my factors equal to 0. Okay, and now I have two little power equations, right? Just like the previous examples. So I'm going to isolate the variable with the exponent in both of them. Okay, then I'm going to change them to radical form. Okay, and then I'm going to cube them to get rid of the cube root. Okay, so here I get y. Okay, and then 4 cubed is 64. Here I get y, and 1 cubed is 1. So there are my two examples, or my two solutions. Okay. So that really combines two different techniques that we've talked about. This is factoring something that's quadratic in form but has fractional exponents, and then that combined with solving these smaller power type equations. Okay, so let's look at one more solve by factoring. Okay, so this is quadratic in form. Okay, so I'm actually going to use substitution by this for this just so that it's easy to see. Okay, it's not just x plus 2, it's x plus 2 squared, right? Because the exponents are squared into the fourth. Okay, that's what we want to have as like our variable. Okay, so this would give me u squared minus 4u minus 12. Okay, and now I can factor this easily. Okay, so I'm looking for things that multiply to 12 and add to -4. So -6 and +2. Okay, and then I'm going to set each of my factors equal to 0. Oops. Okay. You could even isolate the u. Okay. But what we're not going to forget is to go back to our original variable. Okay. So we're going to substitute back in for u. Remember, u was x plus 2 squared. So we're going to substitute in here x plus 2 squared. Okay. And each of these is quadratic equations that we can solve. Okay. So I'm going to square root both. Okay, so I get just the radicand here. And then I'm going to subtract 2 from both sides. Okay, now over here, we're not going to have any real solutions because no real number squares to -2. But remember, we have the possibility of complex solutions. So I'm going to square root both sides. Okay, over here, this simplifies to x plus 2. And over here, I'm going to get root 2i. Okay. And then I'm going to subtract 2 from both sides. Okay, so we'll really get 4 solutions, 2 complex solutions and 2 real solutions. Okay. All right, well, I appreciate you guys watching this video. I know it was a rather long one, but go ahead and try the homework. There's no worksheet associated with this section, so I'll see you guys in the next video.